I do want to start this video by doing a quick review. So we started looking at acids and bases. We looked at Arrhenius theory and then also Bronsted-Lowry. And I'm going to review mostly from the Bronsted-Lowry perspective here. So we defined an acid as a substance that's going to donate a proton to another substance, right? A base is going to be a substance that gains a proton from another substance. So my acid is going to be my proton donor. I'm going to write a couple reactions here. I'm going to use HA as my generic acid, and then I'm going to react it with water, which is a pure liquid. And then if I was looking at a strong acid, it's completely ionized, so I'm not going to draw an equilibrium arrow, right? Every little bit of HA is in its ionized form. So in this case, this is my acid. Water is acting like my base, right? It's accepting the proton to form its conjugate acid, hydronium ions, leaving me with this conjugate base. And then remember, if it's a strong acid, right, it is completely ionized. It's not going back in the other direction. And this conjugate base has no affinity for protons, meaning it's not going to accept protons. Even though I'm calling it a conjugate base, it's not basic. We should have the word for in there. No affinity for protons. Right? If I was to draw my beaker drawing, I have hydronium ions. I have my conjugate base. I have some water. I don't have any HA in there because it's completely dissociated. So this would be an example of a strong acid. We said that weak acids, right? Well, they're still accepting protons, or they're still donating protons to the base. They're not completely ionized, they're partially ionized. So what that really means for us is that my acid is going to donate a proton to that base. It's going to form hydronium ions and my conjugate base. But then my hydronium ions can actually give the proton back to my conjugate base. My conjugate base does have an affinity for protons, often a pretty strong affinity, going back to HA plus water. Water is still a pure liquid. These are still ions in water, so aqueous solution. So labeling everything, my acid, my base in this case, my conjugate acid, wow, and my conjugate base. And this time we have a strong affinity for protons, for hydrogen ions, right? It is going to go back. So one of the big differences between these. My beaker drawing, I draw the worst beakers ever. I do have hydronium ions, I have my conjugate base, I have some water, but then again, it's going back in the other direction also, so I have some HA, right? I have some of my unionized acid in addition to the ionized version. Because this can exist at equilibrium, right? Because it's reversible, if the rate in the forward direction is equal to the rate in the reverse direction, it is at equilibrium, and we can actually write an equilibrium constant expression for it, just like we did in chapter 13. So concentration of products raised to a power equal to their coefficient, so they both have a coefficient of 1, over the concentration of my reactants. Remember that we're leaving pure solids and liquids out of it because water is a liquid, it's not part of my expression. And then instead of putting a C, often we'll put an A here because we're talking about acids. So because weak acids can exist at equilibrium, we can write equilibrium constant expressions for them. And then if we remember chapter 13, right, remember the larger the value for our equilibrium constant, the more equilibrium lies towards products, right? If I have a small value for my equilibrium constant, the more it lies towards reactants. So the bigger my value for Ka, the more products I have, right? That's my ionized form. the stronger the acid. It's still a weak acid. Strong acids don't have Kas, right? If we go back up and look, there's no equilibrium here. So strong acids do not have Kas. When I say if it has a larger value for Ka, it's a stronger acid. It's a stronger weak acid. Looking at bases, which honestly we kind of already did, right? If I go back up, water in both of these examples is accepting a proton to form hydronium ions, right? If you have a Bronsted-Lowry acid, you need a Bronsted-Lowry base, right? The acid's going to donate the proton to something else. So I need that something else to accept the proton. That is my base. I am going to do a couple examples here. I'm going to use MOH. So OH is my hydroxide ion, and then M is just a metal atom. And I have it in aqueous solution, so it is in water. And it's dissociating to form my metal cation and hydroxide ions. And I'm essentially using Arrhenius here when I draw this, but this is my strong base. Remember, you did have a list of strong acids and strong bases that you needed to memorize. All of the strong bases do have hydroxide ions in them. And then, of course, this is not going backwards, right? It's not reversible. I have essentially no conjugate acid when I look at a strong base reaction. If I was to draw my beaker drawing, I do have my dissociated ions. And then I also have some water in here. Do be careful. Sometimes you have a cation from group 2A, so something that would have a positive 2 charge when it forms an ion. So something, if it was like calcium hydroxide, you would actually have 2 hydroxides for every 1 calcium. Looking at a weak base, and I'm going to use a generic B4 base, and I'm going to stick a couple protons on there. I'm going to react it with water. Water is going to act like my acid this time. So this is my base. Water is acting like an acid. And we're going to produce my conjugate base plus my conjugate acid. So I'm just adding hydrogen and a positive charge, right? A proton is being added to that. And then because this is a weak one, that conjugate acid can donate a proton back to that conjugate base, going back to form BH3 in water. And my conjugate acid here, right, this can donate its protons, right? It is ionizable, right? It can donate that proton. If I was to draw a beaker drawing for this one, we'll squish it in over here. I have my conjugate base. I have my conjugate acid. I do have my original base, right? Plus I have some water. And then just like we did with our weak acid, because this is reversible, it can exist at equilibrium. I can write an equilibrium constant expression for this. I'm going to put a B for base this time. As always, concentration of products on top. Concentration of reactants on the bottom, excluding water because it's a pure liquid. The higher the value for Kb, right, the more it lies towards products, the stronger that base. And then remember that acidity and basicity are inversely related, right? The stronger the base, the weaker its conjugate acid, and vice versa. So what we're going to be moving on to in this video is I want to look more closely at water, right? These reactions I did, here I have water acting like a base, right? It's accepting a proton to form hydronium ions. Here I have water acting like an acid. It's losing a proton to form hydroxide ions. So water can act both like an acid and a base. And water's not the only substance that can do that. There are others. And the name for that is amphoteric or amphiprotic. Those two words mean the same thing. And honestly, I do use both. So what these are species that can act like both an acid and a base. So meaning they can donate a proton, they can also gain a proton. And I'm talking Bronsted-Lowry here again. So act both like a Bronsted-Lowry acid and a Bronsted-Lowry base. We should specify that. It's really safe to assume, unless I specify a different theory, I am talking about Bronsted-Lowry. So water is one of those examples. Another example we could do, if I wanted to do bicarbonate ions or hydrogen carbonate, right? I could add a proton to that and end up with a conjugate acid. H2CO3. I could remove a proton from it and end up with a conjugate base, carbonate ions. So because I can both add a proton and remove a proton from it, I would say that it's amphoteric or amphiprotic. I do want to look specifically at water. So we're going to look at the ionization of water. So if I had one water molecule and another water molecule, right? We rarely have one molecule, right? If I had 1 mole of water, which is not very much, right? That would be 18.02 grams of water. I have 6.022 times 10 to the 23rd water molecules. So basically, anytime you have water, you're going to have more than 1 molecule. So what I'm doing here is I'm taking 2 of those water molecules in my sample and I'm reacting them with each other. One can act as an acid, the other can act like a base, and I end up producing hydronium ions and hydroxide ions. These are both pure liquids, these are both aqueous. And then because water is a weak acid, also a weak base, it can go back in the other direction. And this is always happening. If you just have a glass of water, it's not actually just water, right? If I was to draw a beaker drawing of water, I'm not just going to put H2O in there. I'm also going to put hydronium ions and hydroxide ions. So any aqueous solution, it doesn't matter if it's just pure water or if it's a salt solution, I'm always going to have water, hydronium ions, aqueous hydroxide ions, and then if it is a salt solution, I also have that salt in there. So again, anytime you have an aqueous solution, water does this. It's called auto-ionization. It just does it on its own. Water can act like a base, water can act like an acid, and it just does that, right? That's the nature of water. Just kind of looking at structures, it's good to remember every once in a while what these guys look like, right? I don't have 2 hydrogens bonded to each other. I have 2 lone pairs. And then we're going to end up with, this guy would be trigonal pyramidal. I do have a formal positive charge on that oxygen. And then hydroxide with its 3 lone pairs. And the oxygen has that formal negative charge. Which, if you've noticed, I do this a lot. I often write minus OH instead of writing OH minus. And the reason I do that is I know the negative is on oxygen, and it's just easy enough to put it there by moving it to the other side, because that's where it is. So if you remember your formal charge calculation, which I hope you do, from 150, 151, that negative is actually on the oxygen atom. So these guys are reacting with each other, right? Essentially what's happening is one of these lone pairs is grabbing the proton, right? Just the hydrogen ion. Remember, it's accepting a proton, not a hydrogen atom. And that's giving me this, right? I now have 3 oxygen on there and 1 lone pair. And then these electrons, right, are not going with that proton, they're staying. So they actually become that 3rd lone pair on my hydroxide ions. And then it can go back in the other direction also, right? Because it's weak. So again, this is always happening anytime I have water. Because it's at equilibrium, I can write an equilibrium constant expression for this one. So a K of the capital variety, right? Remember lowercase k's are rate constants. And that's going to be equal to the concentration of my products raised to a power equal to their coefficients, so 1 mole of each, and then over the concentration of reactants. However, both of my reactants are pure liquid, so they're not going to be part of my expression. And then we're going to put a subscript W here because it's the ionization constant for water, right? It's my equilibrium constant for water, sometimes called ionization constant. And then at 25 degrees Celsius, which is considered room temperature, this number is equal to 1.0 times 10 to the negative 14th. Remember, it's an equilibrium constant, so I don't actually need units. If I did include them, it would be molar squared. But this is going to be a really important equation. This is going to be the basis for whether or not a solution is considered acidic or basic if you have an aqueous solution. It's also going to be the basis for our pH scale. So again, anytime you have water, it doesn't have to be pure water, it could be a salt solution of water. If something's in water, water reacts with water to produce hydronium ions and hydroxide ions. If you look at this number, right, again, remembering back to everything we learned in chapter 13, that's a small number, right? Remember, if Ka's or Kc's, in this case Kw's, right, if my equilibrium constant is small, and we define small as less than 10 to the negative 3rd, it's mostly reactants at equilibrium. So when I say, right, if you have a glass of water, you actually have all of these things, right? Based on that number, 1 times 10 to the negative 14th, that's definitely small. It's very, very small. It's mostly water, right? It's not a third proportional like that. It's a lot of water and a very small amount of hydronium ions. I can't really put a number there, but we could say lots. I know that's not a real word, but for these ones, small amount. So let's not use lots. A lot. Try to be good. So mostly water, right? That Ka is little, but you do have some hydronium and hydroxide ions in your sample of water. So I had said that this was going to be kind of the basis for if a solution is acidic, basic, or neutral. So if your hydronium ion concentration, and I will write this down here in a minute, so if your hydronium ion concentration is larger than your hydroxide ion concentration, it's going to be an acidic solution. If your hydroxide ion concentration is greater than your hydronium, it's going to be a basic solution. And when those two are equal to each other, it's going to be neutral. So a neutral solution, and I want to make a table. I want to add, we're going to leave a column at the end of our table that we're going to leave blank for now, that we're going to come back and fill in here in a little bit. So we're going to have neutral, acidic, and then basic. And then kind of our first one, if it's neutral, my hydronium ion concentration is equal to my hydroxide ion concentration. If we wanted a heading for this, I have to move my table down. Sorry, poor planning, guys. we could say relative concentrations, relative ion concentrations. So kind of what that means for us, right, is that our hydronium ion concentration then, if it's equal to my hydroxide ion concentration, and when I multiply those two things by each other, right, it needs to equal Kw, right? It always needs to equal that number. That means that my hydronium ion concentration needs to be equal to 1.0 times 10 to the negative 7th molar. And my hydroxide ion concentration needs to also be equal to 1.0 times 10 to the negative 7th molar, right? Because 1.0 times 10 to the negative 7th multiplied by 1.0 times 10 to the negative 7th is equal to Kw here, 1.0 times 10 to the negative 14th. And then our last column that we're going to leave blank for now. If we have an acidic solution, my hydronium ion concentration is going to be greater than my hydroxide ion concentration. What that means in terms of numbers, it's going to be greater than 1.0 times 10 to the negative 7th molar. Hydroxide is going to be less than 1 times 10 to the negative 7th molar. If it's basic, the opposite, my hydronium ion concentration is less than hydroxide, right? My hydroxide ion concentration is greater than my hydronium ion concentration. Hydroxide less than 1.10, hydronium less than 1.0 times 10 to the negative 7th molar. Hydroxide greater than 1.0 times 10 to the negative 7th molar. So again, we're going to come back and add one thing to this here in a few minutes, but I want to do some examples first using this. So if a solution has a hydroxide ion concentration of 2.43 times 10 to the negative 4th molar, what is its hydronium ion concentration? And then also, that's supposed to be a question mark, is the solution acidic, basic, or neutral? So if an aqueous solution has a hydroxide ion concentration of 2.43 times 10 to the negative 4th molar, that's a 4. What is the hydronium ion concentration? And then is the solution acidic, basic, or neutral? And I did write hydroxide and hydronium out using words instead of the atomic symbols on purpose. A lot of times on tests and quizzes, that's how I do it. It's just easier to type out the word than it is to do the symbols with subscripts and superscripts. But a lot of times it confuses people, and I don't mean it to. So just make sure that you keep these guys straight. Like, most people know which is which, but if you see them in print on a test or a quiz and you're hurrying or you get a little nervous, it's really easy to get those two words mixed up because they look very similar to each other. Of course, they'll be typewritten, so they'll look a little bit better, but it's still really easy to get hydroxide and hydronium mixed up when you're just reading the question. So just be really careful. Hydroxide is my OH minus. Hydronium is my H3O plus. So in this problem, I'm saying that my concentration of hydroxide is 2.43 times 10 to the negative fourth molar. And if you read hydroxide here and interpreted it in your head as hydronium, you would actually get it, whether it's acidic, basic, or neutral, backwards. So be careful. And we can actually answer that part of the question first if we wanted, right? My hydroxide ion concentration is 2.43 times 10 to the negative fourth. And if we go up and look at our table, that value is larger than 1.0 times 10 to the negative seventh, right? These are negative exponents. So this number is bigger than that number. So this is actually a basic solution. Larger than 1.0 times 10 to the negative seventh molar. Calculating my hydronium ion concentration, we're just using my Kw expression, right? My ionization constant for water. I know that those two multiplied by each other is always equal to Kw. So I know that 1.0 times 10 to the negative 14th is always going to be equal to my hydronium ion concentration, which is my unknown in this problem, multiplied by my hydroxide ion concentration. So grabbing my calculator, please type this in also. I want to make sure that everyone's using their calculator correctly. You do need to use the scientific notation button on your calculator, or make sure you use parentheses every time you type it in. And I get 4.1 times 10 to the negative 11th molar. So again, this is always going to be true. If we know one, we can solve for the other by setting them equal to Kw. And then based on the relative concentration, right? If I wanted to look, another way to look at it, if it's acidic or basic, my hydronium ion concentration is this number, which is less than this number. So my hydronium ion concentration is less than my hydroxide ion concentration. My hydronium ion concentration is less than 1 times 10 to the negative 7th. So 3 different ways to determine that this solution is actually basic. So this is the basis for a pH scale. pH is going to be this last column on my table. So pH. And be really careful when you write this. The H actually stands for hydrogen ions, and the atomic symbol for hydrogen is a capital H, not a lowercase h. So if you were to write pH, it's actually wrong. Don't do that, right? If you were to write hydrogen is that, it's wrong. I would take off for it. So be really careful. The H in pH needs to be capitalized. The P, it doesn't really matter. It actually stands for like percent or power of hydrogen. If you're starting a sentence and it's the first word of your sentence, then capitalize it. If not, it doesn't have to be. But again, the H must be capitalized. Capitalize. Capital H. So essentially what the pH scale is it's a more convenient way to express the hydronium ion concentration. So our pH scale is just another way to express the hydronium ion concentration we can spell here in solution. So if I was to ask you what's pH, it's a way to express the hydronium ion concentration in solution. That's what it's doing. And then based on the hydronium ion concentration, right, if we go back up, we can tell whether or not a solution is acidic, basic, or neutral. So instead of writing it in scientific notation like this, it's a different way to express it that tends to be more convenient. So mathematically, right, how we're going to get to it is my pH is actually going to be equal to the negative log, and be careful, it's log base 10. We used a lot of logs in chapter 12, but they were natural logs. This is log base 10 of my hydronium ion concentration. And then if you knew your hydronium ion concentration and you wanted to go backwards, if you knew your pH and you wanted to go backwards to calculate your hydronium ion concentration, it would be the anti-log. So 10, because it's log base 10. And then again, be careful, there is a negative here, right? It's the negative log. So to the negative of my pH. So take 10 and raise it to the negative of your pH. So an example, right? If I had my neutral solution, my hydronium ion concentration is equal to 1.0 times 10 to the negative 7th molar, right? What is my pH? So we're going to take the negative log of 1.0 times 10 to the negative 7th. Log values don't have units, so when I express my pH, I'm not going to have units on it. Just be really careful, because if you're going backwards, if you know the pH, it's not going to have units, and you're calculating your hydronium ion concentration, that does need to have units, right? Remember, those brackets mean molar concentration, so you do have to put that capital M on there. So just really watch out for units. Remember, our values for our equilibrium constant, well, they often have units. We don't have to show them. Here, I don't actually have units. Log values are unitless. We can add that. No units for pH. I'm going to write NPOH. I haven't shown you that yet, but it's just going to be the negative log of my hydroxide ion concentration. It's also a log value, so it's not going to have units. We're just going to add that here for completion, and then I don't have to rewrite it later, and you don't have to rewrite it later. So back to my problem. I'm going to take the negative log and of 1.0 times 10 to the negative 7th. There's a decimal point here. And I'm going to get, just bear with me on sig figs, you guys actually get a new sig fig rule here. I'm actually going to get 7.00. When you type it into your calculator, you're probably just going to get 7. But remember, your calculators don't know significant digits, and we do need to pay attention to significant digits. So this is the correct answer. I know at first glance, it's really easy to look at it and think my sig figs are wrong, but they're not, right? I have 3 digits here, so you would think 3 significant figures. This decimal point makes both of those significant. If you look here, you have 2 significant digits, so it seems incorrect. It's actually not, and this is our new rule. This 7, right? This 7 is coming from this exponent. If I was to take the negative log of 1.0 times 10 to the negative 2, I'm going to get 2. If I take the negative log of 1.0 times 10 to the negative 12, I'm going to get 12. I'm ignoring sig figs on those 2 for the minute. I just want to make the point that this 2 comes from this 2. This 12 comes from this 12. This 7 is coming from this 7. Those do not count for sig figs, right? If I give you this number and I ask you how many significant digits does it have in it, you're just going to tell me 2, right? You're not going to count that negative 7. So this doesn't count for sig figs. So this, because it comes from that, doesn't count for sig figs. So if I want 2 significant digits in my answer, right, for my pH, I need to have 2 digits after the decimal point. So for log values, any digit to the left of the decimal point come from the exponent in your original number, so they are not going to count. So this needs to be 0, 0, this needs to be 0, 0. If I did negative log of 1.000 times 10 to the negative 8th, I'm actually going to get 8. I have 4 significant digits here. That 8 does not count, so I need to go and add 4 zeros after that decimal point. So let's try to write that in some words that make sense. So for log values, only the digits to the right of the decimal point wow, that just got messier. Count for significant digits. So not only do they not have units, but the sig figs are a little bit different than what we're used to. We haven't had a new sig fig rule here in a while, so it's good to have one. New rule. And a smiley face. So do watch out for that. So I'm going to go back up to our table here. If it's neutral, we just calculated that. My pH is going to be 7.00. And it's going to be exactly 7.00. If it's 7.01, it's not 7, right? It's bigger than 7. If it's 6.99, it's not 7, it's 6.99. So if it's neutral, my pH is going to be 7.00. Because my hydronium ion concentration, right, is going to be 1.0. It's not going to be 1.01. If it's that, it's greater and it's actually an acidic solution. So do be careful. And then I guess the other thing I want before we finish our filling in our table here is this negative exponent, right? Because there's a negative here, the bigger this value is, the smaller my pH is going to be. So something that's acidic is going to have a higher hydronium ion concentration. If I go back up to my table, right? If it's acidic, so I'm right here, my hydronium ion concentration is bigger. However, my pH is going to be lower because pH is the negative log of that. So the more hydronium ions you have, the smaller your pH is going to be, right? We're raising it to the negative value. Sorry for all this scrolling. So if it's acidic, my pH is actually going to be less than. Just be really careful. Hydronium ions is bigger, pH is smaller, it's the negative log. And then if it's basic, my pH is going to be greater than 7.00. That inverse relationship between my hydronium ion concentration and my pH. We could actually write pH negative, we'll circle it, log. We can also look at what's called the pOH. I mentioned this briefly a few minutes ago. And the pOH is similar to pH, but instead of the negative log of hydronium ion concentration, it's the negative log of our hydroxide ion concentration. If I knew my pOH and I wanted to calculate hydroxide ion concentration, 10 to the negative pOH. And then again, because it's the negative log, the larger your hydroxide ion concentration is, the lower your pOH. So another equation for us. We could actually add another column to this table if we wanted. We could add pOH. Again, it's going to be unitless, only values to the right of our decimal point are going to count for significant digits. If it's neutral, it's still going to be 7. Your pOH plus your pH are going to equal 14.00. My pOH, if it's acidic, is going to be greater than 7. It's that inverse relationship I was just talking about. And then less than 7. Right? The larger your hydroxide ion concentration, the lower your pOH is going to be. I feel kind of at this point we should do a quick summary of all of our equations. We have them in one spot because I have them kind of scattered all over. So let's just do a summary of equations. And then we'll do some example problems. So we know that hydronium ion concentration multiplied by hydroxide ion concentration is always going to be equal to Kw, which at 25 degrees Celsius is 1.0 times 10 to the negative 14th. I know that my pH is the negative log of my hydronium ion concentration. And then of course, if we wanted to go backwards, 10 raised to the negative pH, and then just substitute OH. And then we could add one more. If I was to add my pH to my pOH, I said this one a couple minutes ago, but we haven't written it yet, I actually get 14.00. So kind of a summary of what we have. So let's look at some examples. What is the hydroxide ion concentration of a solution if its pH is 3.24, and then is the solution acidic, basic, or neutral? So again, I'm spelling out hydroxide on purpose just to get you used to looking at it. So we know that our hydroxide ion concentration, right, is my OH minus concentration. That's what we're trying to solve for. We're given a pH of 3.24. The second question, acidic, basic, or neutral, my pH is less than 7, so it is acidic, which means when I calculate my hydroxide ion concentration, I'm going to expect that to be less than 1 times 10 to the negative 7th molar. So this one, we can do it a couple different ways. If you wanted, right, I'm going into my equation sheet, you could do this, right? We could subtract the pH from 14 to get my pOH, and then use this equation to get my hydroxide ion concentration. The other way to do it is we could use this equation to figure out my hydronium ion concentration. I forgot a positive charge here. And then once I have that value, we can use our Kw expression to figure out our hydronium ion concentration. Either way is going to work, whatever your preferred method is. I'm going to use the pH plus pOH one because we haven't used that equation yet. But again, you could use either one. So the way I'm going to choose to do it, I know that 14.00 minus my pH is going to be equal to my pOH. So calculator, you could probably do that one without a calculator. And then once I have that value, my hydroxide ion concentration is going to be 10 raised to the negative of that. So calculator again. Make sure you type in that negative. And then just be really careful for your significant digits here, right? How many significant digits should I have in my answer? Let's do that first before I write down the answer. What are you guys thinking? So the answer is 2. If you didn't get that, that's okay. We're still learning. You'll get it worked out by the time we have our first test. But remember, only the digits after the decimal point for log values count. So 3.24 is actually only 2 sig figs. Here I'm subtracting, so 2 after the decimal place. This is also only 2 sig figs, right? However you want to look at it, this doesn't count. So 2 digits here, I want 2 significant digits in my answer. So I actually get 1.73, but I only want 2 significant digits times 10 to the negative 11th. And then don't forget units, right? I am solving for hydroxide ion concentration, so I need to throw that capital M on there. It is kind of like the value makes sense to me, right? Remember, because it's acidic, I want that hydroxide ion concentration to be less than 1 times 10 to the negative 7th molar, and it is. Just quickly doing it the other way. I said you could do it either way. The other way to do it, I would take a 10 and raise it to the negative of my pH. So let's do that real quick. Again, don't forget to type in the negative. Oops, I forgot the decimal point. And I get that my hydronium ion concentration, again, just 2 significant digits, so 5.8 times 10 to the negative 4th molar. And then I know that if I take Kw, right, I'm just using this one here, and I divide it by my hydronium ion concentration, I'm going to get my hydroxide ion concentration. So I'm just typing this into my calculator right now, and I get 1.7 times 10 to the negative 11th molar. So again, either way works for us.